All right, so now we are moving away from exponential functions to logarithmic functions, but there's a reason why these are often put near each other. It's because they are what we call inverses of each other. So what I want to start out with is figuring out what does the graph look like for the exponential function 2 to the x, and show you how that turns into its inverse, log base 2 of x. Okay, so these are inverses of each other. Other examples of inverses would be like 3 to the x and log base 3 of x. What you will notice is that eventually if I make a graph for 2 to the x and I make a graph for log base 2 of x, they're going to have all the same points, but with all the x's and y's switched. So let's start with 2 to the x. So y equals, 2 to the x. I'm going to graph it on the domain from -2 to 2. So at -2 it's at 0.25, -1 is at 0.5, 0, 1, 1, 2, and 2, 4. Okay, so I'm going to actually start by graphing that function, and I will graph it in pencil so that we have things in different colors. Okay, so we're plotting -2.25, -1.5, 0, 1, 1, 2, and 2, 4. Okay, this is the exponential function. So I'm going to label this as y equals 2 to the x. All right, so now eventually I'm going to show you how you could type this in your calculator, but just in case you can't, this is where the log graph originally came from. You're taking all your x and y's from your exponential and you're switching them. So I would start with 0.25, -2, 0.5, -1, 1, comma 0, 2, comma 1, 4, comma 2. So now I start plotting them. 0.25, comma -2, 0.5, comma -1, 1, comma 0, 2, comma 1, 4, comma 2. You're going to notice that this is the exact same graph as you have with the exponential, but it's been reflected over the line y equals x. All of the x's and y's have gotten switched. So if you remember from when we were dealing with an exponential function, the asymptote was the equation y equals 0, the x-axis. Okay, the domain of the exponential was all real numbers. Okay, and the range of a basic exponential was y is greater than 0. It was always located above the y-axis. Well, now think about all of these x's and y's getting switched, and now you end up getting the information for the logarithmic function. Okay, so the domain is no longer going to be all real numbers. The domain is going to switch to what the range was. This is my description of x's and y's getting switched. So instead of y is greater than 0, this becomes x is greater than 0. Is that true? Look at this graph right here. Okay, what kinds of numbers are we plugging in? Only positive numbers. We can't plug in 0, we can't plug in negatives, or we don't get any of that log graph. The range is the opposite of the exponential, okay? These are getting switched, so now my range is all real numbers. Does that make sense? Yeah, as this goes all the way down, it goes towards negative infinity. I know this is going up slowly, but it's going up forever, so the range is all real numbers. The asymptote of the exponential was y equals 0. The asymptote of the logarithm is x equals 0, which is the y-axis. Okay, so again, everything from the exponential gets switched x and y to become the logarithm. Now just so you know, if you wanted to graph log base 2 of x in your calculator, if you hit math, you scroll from the bottom to log base 2 of x. Okay, and then if you take a look at that graph, you'll end up seeing the same kind of graph that we have here. It just looks a little weird on the calculator because it looks like it is touching the y-axis, but it's really not. Okay, so this is important. The fact that the domain of the logarithm is x is greater than 0 is one of the big ideas that's important for a logarithmic function. You can't plug into a log something that's negative or 0. So what I want to do with the next couple of examples is just state the domain and range. Okay, so the easy part with all of these is that the range is going to be all real numbers for every single one of these situations. No matter what, it's always going to get all the way up to infinity, all the way down to negative infinity. It's the domain that's going to have issues. Okay, so you take what's inside that logarithm and you guarantee that it stays positive. So this is really actually just a basic log graph. It just happens to be a decreasing one instead of an increasing one. But at the same time, you take what's inside the log, you make sure it stays greater than 0, and that would be the domain. So if you look at the next one, this says log base 2 of x plus 4, but that plus 4 is added on to the end. That's shifting up or down. If I shift this graph up or down, does that change the domain? No, I'm still not going to be able to plug in 0. I'm still not going to be able to plug in negatives. It's only left and right shifts that are going to change the domain. So my domain here is still taking what's inside the log and making sure it stays greater than 0. That plus 4 was not inside the log. Last but not least, look at the third example. This time I have now an entire expression inside that log. Make that expression stay greater than 0, solve that inequality, and this now tells you that your domain has to be values bigger than 3. If you want to check this, type in your calculator log base 2 of x minus 3 and take a look at your table. Okay? When you plug in numbers that are bigger than 3, you're getting a value. But if you try to plug in 3, you're no longer getting a value. And if you plug in anything less than 3, you're no longer getting a value. That's because it's undefined when x is not greater than 3. Okay? Okay, properties of logarithms. I know this is one of those topics that everybody doesn't really seem to love so much. Honestly, it's just formulas to memorize, but I can understand how it gets a little confusing with the subscripts and the exponents, so I'll try to keep it as basic and straightforward as possible. So you have 3 different rules that you're going to be applying with these logarithms, and the goal is going to be to condense them to a single logarithm. That's going to be useful in our next lesson when we solve log equations. So as long as you have the same base, if it's log x plus log y, you can combine them together as one logarithm where x is being multiplied by y. Essentially, by the way, what you're doing is you're doing the reverse of exponent properties. If you remember when you were doing x squared times x to the third, you would add your powers. Well, now reverse that. You're adding, which is becoming multiplication. In a similar fashion, if the quotient rule is log x minus log y becomes log x over y. The way that I like to remember it is that if something is a positive log, then whatever its variable or number goes in the numerator. Anything that's a negative log, its variable or number goes in the denominator. And you'll see me apply that a little bit later in some of our examples. The last thing is the power rule, and this can be written in both ways. An exponent can be dropped down in front, or a coefficient can be raised up to be an exponent, and in both cases you'd be having equivalent expressions. So if I want to be condensing logarithms, the first thing I want to do is get rid of any coefficients, raise them up to be exponents. So I'm going to just start by rewriting this as log base 3 of x, log base 3 of y, and I'm going to take that 2 and raise it up, so I'm going to make that log base 3 of z squared. Okay, so now when I combine this to one single logarithm, it's one single logarithm, and generally I usually like to put a fraction on the inside. Positive log x means x goes in the numerator. Positive log y means y goes in the numerator. Positive log z squared means z squared goes in the numerator. So technically I don't need a denominator in this case. You could put a 1 there just to play it safe, but that would mean your final answer is x, y, z squared inside log base 3. Okay, so now we start getting into some ones that have negatives, and that's why I talk about making that fraction. First of all, any coefficient should be raised up to be exponents. So this 4 is going to raise up to become log base 7 of z to the 4th. This is really a 1/2, that 2 that's there is really a 1/2 that's in front of that log z. So I'm going to take that 1/2 and I'm going to raise that up to be an exponent. So that's going to become log base 7 of z to the 1/2, and then a little bit later I'm going to rewrite that as log base 7 of z square rooted, okay, because that's what anything to the 1/2 power is going to be. So now I'm going to condense to make one single logarithm, log base 7. Okay, inside that log you're going to make a fraction. Positive log z to the 4th means z to the 4th goes in the top, and negative log z to the 1/2 means the square root of z goes in the bottom. If you want to get super technical, technically I guess you could combine your exponent properties, but I'm just going to leave this as like this for right now, okay, because I just wanted you to practice with condensing it to a single log. Okay, number 3, you're going to start by raising up all of your coefficients to be exponents, and I would highly suggest you rewrite it as a separate step. The more you do at once, the more likely you are to make mistakes. So this is going to become log base m of x to the 2nd, log base m of y to the 3rd, log base m This is really going to be z to the 1/2, so I'm going to write that as the square root of z. Okay, that's anything to the 1/2 power. And then minus log base m of w to the 4th. Okay, as I combine these to one single logarithm, it becomes log base m, and then I think about if I'm putting things in the numerator or denominator based on if they're positive or negative. Positive log x squared goes in the numerator. Negative log y cubed goes in the denominator. Positive log square root of z goes in the numerator. Negative log w to the 4th goes in the denominator, and that is my condensed expression. Okay, one last one. I'm going to start by distributing the negative 1/2 inside the parentheses to get rid of those parentheses. I'm going to have 2 log base 2 of x minus 1/2 log base 2 of y plus 1/2 times 4 is 2 log base 2 of z. Raise all your coefficients up to be exponents. So this becomes log base 2 of x squared minus log base 2 of the square root of y plus log base 2 of z squared. Combine this to one single logarithm and put a fraction on the inside. Positive log x squared goes in the numerator. Negative log square root of y actually goes in the denominator. Okay, I should use a pencil. And positive log z squared means z squared goes in the numerator, and that is my final condensed expression. Okay, so positive log numerator, negative log denominator. Okay, getting into solving log equations. There's going to be two main types of log equations to solve. You're going to have the kind where you have a log on both sides. Now it's important that it's only a single log on each side. So if you have more than one log, you're going to have to use our log properties like we talked about in the previous lesson to condense things to a single logarithm. So if it turns out that you have two logs on one log on each side, and they both have the same base, okay, and they're totally condensed, so it's not more than one, you'll be able to drop the logs and set the insides equal to each other. And then all you have to do is finish solving this equation. So I'll plus x to both sides. This gives me 8 equals 4x. Divide both sides by 4, and this gives me 2 equals x. Now, this is very important. With log equations, you always have to check your answers. What you need to really check is to make sure that the answer you're getting isn't making something inside of one of the logs 0 or negative. If you remember the domain of a logarithm, okay, here's a basic log graph. A domain of a logarithm is x is greater than 0 for any log base b of x. Okay, so anything that's being plugged inside of a log has to be positive and not 0 and not negative. So if I plug in 2, negative 2 plus 8 is positive, 3 times 2 is positive, so this is going to work out just fine. Okay, and I'll show you some examples where it doesn't work out. All right, so type 1, log on each side. Type 2, log on one side. You need to make sure it's a condensed log. It can't be like log plus log or log minus. It can't have any coefficients. Once you get it to this, you're going to use the ability to rewrite logs as an exponential function to be able to solve this. So the way you do that is you take the base of the log, you raise it to the power on the other side, and you set it equal to everything that's inside of that log. So 4 to the second equals everything on the inside, n minus 6. 4 to the second is 16, equals n minus 6. As I plus 6 to both sides, I get 22 equals n. Again, don't forget to check. Does 22 make what's inside the log a negative or a 0? The answer is no, so that's going to work out, and therefore your answer would be n equals 22. All right, so let's look at some examples. I said make sure to condense to a single log on one or both sides if there are more than one. So on this left-hand side here, log base 4 of 3x squared minus log base 4 of 3 equals 5. This needs to be condensed to a single logarithm before I can use either of the kinds of methods that I talked about above. So I connect them. Log base 4, remember we make a fraction. Positive log means 3x squared goes in the numerator. Negative log means 3 goes in the denominator, and that's all equal to 5. If I want to simplify this a little bit, these 3's could cancel, so I'd have log base 4 of x squared equals 5. So you can see this is the type 2 kind of problem where I have it so that it's only a log on one side, no coefficients. I've already condensed everything, so I'm going to rewrite it as an exponential. 4 to the 5th equals x squared. 4 to the 5th, hang on one second, 4 to the 5th is 1024 equals x squared. If I want to undo an x squared, I take the square root. Remember, there's a plus or minus version when you take a square root. The square root of 1024 comes out to be 32, so plus or minus 32. All right, so now let's think about these solutions. X equals 32 and x equals negative 32. Okay, do both or one of these solutions work? You've got to make sure it does not make what's inside the log a negative or a 0. So what's actually very lucky in this problem, when you plug into something like x squared, 32 and negative 32 are technically going to come out to be the same thing. So actually in this problem, both of your answers are included, plus and minus 32. Okay, if it happened that that was like x cubed and you were now making what was inside that log a negative, then it would have to get rejected. But in this case, both those answers work, so that's why you keep both the plus or minus 32. All right, let's see one where I have to do a little bit of rejecting. So you'll notice that I have to condense my logs together on the left-hand side. This becomes log base 10. As I condense together, this becomes x plus 8 in the numerator times x in the numerator. There's no subtraction, so there's no denominator, so I'm just going to leave it like that. On the right-hand side, I have log base 10 of 20. Okay, this is the kind like I have in type 1 where I have like a log on each side. I'll be able to drop these logs and set the insides equal. X times x plus 8 is equal to 20. So now I have a quadratic. So quadratics, you know, you want to get it equal to 0, factor, and then solve for all your solutions. Distribute x inside this parentheses, so I have x squared plus 8x equals 20. Get the whole thing equal to 0, so minus 20 on both sides. X squared plus 8x minus 20 equals 0. This is an AM trinomial. There's nothing in front of x squared. It's a trinomial, so it's not dots. There's no GCF. So I want to find two numbers that multiply to 20 and add up to 8. Remember, if you ever get stuck, you go to y equals. You take the number you want the factors of divided by x and take a look at the table. Okay? 2 and 10 are two numbers that multiply to 20 and add or subtract to be 8. So 2 and 10. They're multiplying to be a negative, so they're opposite signs. And then the middle sign is what goes to the larger number. So positive 10, negative 2. As I finish solving, this would give me x equals 2 and x equals negative 10. As I said before, log functions, log equations, oftentimes there's something that's going to have to be rejected. So if you take a look, 2 plus 8 would be 10, that's positive, 2 is positive. Negative 10 plus 8 would make what's inside of this log a negative, so this has to get rejected. And then my final answer is only x equals 2.